velocity problem. So 2.1, we had covered tangents and velocities. Now we're looking back at velocities. And then along with that, other rates of change. So it's important for you to realize finding a slope, and you learn this in Algebra 1, but sometimes you don't totally relate the two ideas. When you learn about slope in Algebra 1, you also learn about rates of change, and you should be making the connection that a slope is a rate of change. It's a change in y values over a change in x values, therefore a rate of change. So velocity is also a rate of change. It's a change in displacement over a change in time. So that's why finding slopes of tangent lines and then finding velocities we saw in 2.1, it was the same process as a limit, because they're both rates of change. And therefore, that's how any rate of change fits into this same scenario, because slopes of tangent lines are just slope in general, and then velocity, they're rates of change. So the idea that we had talked about in 2.1 with velocities, sorry, that kind of got cut off by the hole punch, but the idea was that, and I'm going to put in parentheses instantaneous velocity. I'm just putting instantaneous in parentheses. So whenever you're asked to find a velocity, it is assumed it is talking about instantaneous velocity. If it wants average velocity, it will say average in front of velocity. So average is specified in the problem. If it just says find the velocity, it means instantaneous. So instantaneous velocity, the idea was this was the limiting value of average velocities over shorter and shorter time periods. So you might remember we're actually going to revisit the same problem we looked at in 2.1, but it said find the velocity after 5 seconds or at 5 seconds. And so we said, okay, if we have a 1 second time interval from 5 to 6 seconds, we found the average velocity. And then we shortened the time interval to 1/10 of a second. And then shortened it to 100th of a second, thousandth of a second, and found the limit of all the average velocities. We no longer need to do that process because we know how to work with limits. So to show you how this is fitting into what we did with tangent lines, it says suppose an object moves along a straight line according to an equation of motion, and they usually use s as the variable that describes position. So s equals f of t. So s is the displacement or the directed distance of the object from the origin at time t. And the function f that describes the motion is called the position function of the object. So then we have in the time interval from t equals a to t equals a plus h, then it's giving us what the change in position would be. So it'd be the function value at a plus h minus the function value from the start at a. And that's shown here. So it's saying we're starting at t, or here's where t is equal to a, here's where t is a plus h. So that displacement, that change in position, is subtracting those two function values. And then the average velocity over this time interval would be calculated by taking the displacement, the change in position, over the change in time. So our displacement was the f of a plus h minus f of a over, and the change in time, well, what would the change in time be? Just h, yes, because we're going from a plus h and then subtracting a, so then it would just be h. This should look familiar to you. This was the slope of a secant line. So then if we compute average velocities over shorter and shorter time intervals, meaning we let h approach 0, because your x values would approach a, we define the velocity or instantaneous velocity v of a, so at time a, to be the limit of the average velocities. So v of a would be the limit of the average velocities, this expression here, as h approaches 0. Which is the exact same limit we were just working with for slopes of tangent lines. So again, in 2.1, we saw they were the same process. Here we're just seeing why they're the same limit. Now, this also means, though, this one is just used most often, but you could also use the limit as x approaches, it would be t. I'll use, x or t. But the limit as x approaches a of f of x minus f of a over x minus a. So that first limit we talked about with slopes of tangent lines, that would still apply here to velocity. What you need to understand is I could give you one problem with a function and say find the slope of the tangent line at this a value, and then give you another problem with the same function and say find the velocity of this function at the same a value, and you're doing the exact same thing for both questions. So you need to understand slope of the tangent line and then instantaneous velocity are the exact same limits. They're the same process. If you graphed a position function and found the tangent line, that's what you're finding is the velocity. So in example 1, like I said, this is revisiting the example we did look at in 2.1, so you don't have to, look back at 2.1 when we did this, but if you do ever look back, it's the same problem, but we can get to our answer by not having to find all of those average velocities. So the problem was supposing a ball is dropped from the upper observation deck of the CN Tower, 450 meters above the ground, and we were given this function here for the distance in meters fallen after t seconds. So this is representing the position after t seconds. And it says, what's the velocity of the ball after 5 seconds? So really you are looking for v of 5. However, like I was just stating as I was going through example or problem 11 from the assignment, I'm actually going to find v of a first. I'm going to find it as a formula and then just substitute 5 in at the end. You don't have to do that. You could substitute the 5 in for a right away. So I'm just showing you an alternate way. And I'm going to use the limit with h. So I know this is going to be the limit as h approaches 0 of f of a plus h minus f of a all over h. And I have my function, f of t is 4.9 t squared. So f of a plus h is replacing the t with a plus h in the function. So I have the limit as h approaches 0 of, that would be 4.9 times the quantity a plus h squared. So that's f of a plus h minus f of a is replacing t in the function with a. So that would just be 4.9 a squared. And that's all over h. Questions there? Because once you set it up, now it's using algebra to simplify the numerator. So limit as h approaches 0 of, I'm going to leave the 4.9, and I'm going to expand a plus h quantity squared. So that would be with FOIL, a squared plus 2ah plus h squared. And then I still have minus 4.9 a squared. And notice, I know I've talked about this before, notice how I'm still carrying down my limit as h approaches 0. So you need to continue writing that. We haven't actually taken the limit yet, so continue including the limit as h approaches 0. I can distribute the 4.9, so that'll be 4.9a squared plus 9.8 ah plus 4.9h squared, and then I still have minus 4.9a squared all over h. I have two terms that don't have h. They cancel out. 4.9a squared minus 4.9a squared. So those are gone. And that means with what's left in the numerator, I can factor out an h. And that would leave 9.8a plus 4.9h all over h. H's cancel out. So then if I substitute 0 in for the remaining h, my velocity after a seconds is 9.8 times a. So this is, again, your v of a. And now, ultimately, I wanted the velocity after 5 seconds. I just have to then replace the a with 5. So v of 5 is 9.8 times 5. You substitute 0 in for the h. Yep, so anything that's still left with h is going to become 0. And then 9.8 times 5 is 49. And what would the units be on the velocity? Meters per second. Yes. You can, unless if a question, I do want to see, I believe I've asked questions like to use the definition. Well, we'll get there when we get to derivatives, but to use the definition. If it says use the definition, I want to see the limit. But otherwise, if you know the shortcut, yes. You'll learn the shortcut, just not right now. I don't know why he knows it, but if he knows it, good for him. You won't appreciate the shortcut if you never have to know the long way. Right? It is good logic. All right, now, with this also, to explain the importance of just leaving a as a, you wouldn't have had to do that. But if you needed to find multiple velocities, so after 5 seconds, after 10 seconds, after however many seconds, rather than doing that limit over and over and over again, you can do it once and then just substitute all of your times into your velocity function. You're basically coming up with a function here for velocity at any time a. All right, but then part B, you might be asked additional questions about this. It says, how fast is the ball traveling when it hits the ground? Well, what would be 0 if it hits the ground? Well, after it hits the ground, so it's asking at what speed does it hit the ground. Well, yes, after it's on the ground, yes. Well, the answer is not 0. So as it hits the ground. All right. Kai had how to solve part B. Kai looked out it. Kai, can you explain what you had said? So if the function is how far the ball has fallen, once it has hit the ground, that means it has fallen 450 meters, since it started at 450 meters. So to find the time it hits the ground, you would set your function equal to 450. Because ultimately, to know how fast it's traveling when it hits the ground, you need to know when it hits the ground. So set 4.9t squared equal to 450. And this is important too. A lot of the time when something hits the ground, you say the position is 0. But in this instance, it's because the function represents how far it has fallen. So if it hits the ground, it hasn't fallen 0 meters. It's fallen 450 meters. So to solve for t, I would divide by 4.9, which I will do this. I want to show you something also, though, on your graphing calculators if you have them handy. That's not the shortcut. Don't get caught up on the shortcut. Now, when I take the square root, remember, anytime you take a square root, you do have a positive and a negative, but a negative would not make sense in this instance. It's a time. So t is going to be the positive square root of 450 over 4.9. Now, what I want to point out to you with this is when, and you probably heard this before, whether it's in a math class or a science class, but you should not round anything in the middle of a problem. So either you want to keep t written this way, and now if this is the time it hits the ground, I can substitute it into my velocity function. See, so now this is helpful because I don't have to go through this process again. But I can substitute it into this velocity function to find the velocity. So I would be finding v of the square root of 450 over 4.9. So that's going to be 9.8 times the square root of 450 over 4.9. 4.5 what? Where are you getting 4.5 from? Oh. All right, so in doing this, what should you be rounding your answers to? 3 decimal places at least. You don't need to worry about sig figs. 3 decimal places. So it's about 93.915 meters per second. Now, another thing you can do on your calculators. Has anybody ever stored a value on your calculator? Okay. So, if you, or even on your graphing calculator, if you haven't done it on your graphing calculator, another thing you could do is you could store what the square root of 450 over 4.9 is, and then just use that to substitute in and multiply by 9.8. So you type in the number first, so I would do the square root of 450 divided by 4.9, hit enter so that your calculator gives you a value. So this is the number that you do not want to round and then substitute in a rounded answer because it can change your answer in the end and then you would get it wrong on the AP test.
Just do second quit.
Yeah, do second mode to quit. Otherwise, I don't know. Okay, and then you leave that there. Right above your on key, you have a key that says STO with an arrow. That's store. So you hit that key. And then you choose whatever letter you want to store it as. So if you wanted to store it as A, notice if you hit your alpha key, like mine is green, and I have the letters of the alphabet in green above different keys. So you hit alpha and then whatever key that represents the letters. So if I hit math, could store it as A. And then you hit enter. So now if I just type in like alpha math, if I just type in A and hit enter, it'll give me that number.
Wow.
I know, right?
To,
Well, so that number will stay stored as X until you store something over it. You use this key? No. Like, you're worried like if you're typing in a function, X is going to be that number? It won't be. It'll still be a variable, yeah. All right, so then if I did 9.8 and then times A, then it'll give me the 93.915. And that'll stay as A until you store something over it. I mean, you can reset your calculator, but...
Wait, so it'll always be that until you...
Yeah, so like I clear this, I turn my calculator off, I turn it back on. It's going to tell me I need to charge my battery. And then, I know, I type in A again, it's still there. I know.
I'm going to store a different value.
Go for it. Just make sure you're not rounding until the end. All right.